we come over to the third column, the number that we're going to need to break the carbon-carbon bond is right here. So this number, 371. So we need plus 371. And then the bond that's being formed is over here, the first column. .352, so that value is going to be negative. So we're releasing energy. So the delta H for this reaction is going to be the energy that you're putting in, then subtracting out the 352. So overall you're getting plus 19 kilojoules per mole for number 5. This is exam 3 review for spring 2019 Organic Chemistry 1. Looking at substitution reactions using free radical or SN1, SN2. So question number 1 is asking you which two compounds ionize with loss of bromide ion to form the same carbocation. So the first thing you want to look at is of these compounds, the hybridization of the carbon bearing the bromine. So compound 1 is sp3, 2 is sp2, 3 is sp2, 4 is sp3. So we learned that in ionization reactions, the carbon bearing the leaving group must be sp3 hybridized. So compounds 2 and 3 can be eliminated. So therefore, if we show the actual ionization reaction, we'll see that 1 and 4 are the two compounds that when bromine leaves, we form an allylic carbocation that has resonance. And so that same carbocation can form from compound 4. When that bromine leaves. So essentially compounds 1 and 4 both ionize to give the same carbocation. Compound 2, what is the expected product of the following free radical substitution reaction? So you're given a 1,4 disubstituted benzene derivative, and what I'm going to do first is determine the unique sets of hydrogens. So I'm going to put just a dot by each unique set. So we have 1, these are then the same, that's 2. These are different, they're the same, that's 3. We have 4, 5, 6. We have 6 unique sets of hydrogen. And now what we need to determine is that under bromine and light, we're going to do a free radical substitution. So one of these hydrogens is getting substituted. And what we can do is eliminate the hydrogens that are bound to sp2 hybridized carbon. And so I'm eliminating those. And from here, if we classify the remaining, we have primary benzylic, secondary benzylic, secondary, and primary. So we know that bromine's more selective, so it's going to go over for a secondary CH bond over a primary, so we can eliminate these choices. And of the two secondary, we know that secondary benzylic is more stable because of resonance stabilization with the aromatic ring. So therefore, one of these hydrogens is going to get substituted. So the answer is A. Question 3 is asking which of the following arrow-pushing formalisms best represents the hydride shift to the more stable carbocation. So first thing we want to do is classify the carbocations that are given. We have tertiary, that's pretty stable. We have secondary, and then for D we have secondary. So we can eliminate A because it's already tertiary. We can eliminate C, even though that's depicting a hydride shift. It's the carbon that is shifting the hydride is too far over from the carbocation. B is showing a methyl group shift, so that's not correct either. So the correct answer is D, and when this shift happens, you would get the following carbocation. So it's going from secondary to tertiary. Question 4 is asking how many stereoisomers are there of 2,3-difluorobutane? So the easiest thing to do is draw that out. So there's butane. There's 2,3-difluorobutane. We have 2 stereogenic carbons. So 2 to the 2 is equal to 4 possible stereoisomers. However, if you analyze these, and the easiest way to do that is in the Fisher projection. And then put in the substituents. So for example, H, fluorine, H. Then we use a mirror plane to show it's an enantiomer. So there's 2. Now we're going to draw diastereomer. We can see that of this diastereomer, there's an internal mirror plane. So this is a meso compound. And so if you did a 180-degree rotation, you would get the same compound. So this actually does not have an enantiomer, so the correct answer for this one is 3. So compound 5 is asking, what is the delta H for the following reaction? So we have a chlorine radical, and if you pay attention to what's happening, I'm going to draw this in a slightly different way. There is the above molecule depicted in this convention. The chlorine radical is actually abstracting a methyl group. So we know that from the product here. So if we were to show that with arrows, we would have chlorine abstracting a methyl group. That's forming this secondary carbon radical. And then we're forming methyl chloride. So what we have to do is look up the bond association energies for cleaving a C-C bond and then forming a C-Cl bond in methyl chloride. So if we go back to the bond association energy table, so the answer for this one is A. Number 6 is, why do polar aprotic solvents increase the rate of an SN2 reaction? So if you think about the reaction coordinate of energy versus time, if you're lowering the energy of activation with a polar aprotic solvent, the most reasonable choice for this is you're making the anion more reactive. The correct answer is B. A is wrong. Aprotic solvents have high polarity. That's, again, a factor of having a polar bond within the molecule itself. Answer C says aprotic solvents better solvate the leaving group and therefore accelerate the reaction. This would be a better explanation for SN1 rate enhancement. D states aprotic solvents raise the energy of the products and therefore accelerate the reaction. So that's not necessarily true as applied to what this question is asking. Question 7. Which of the following hydrogen atoms would most readily be abstracted to generate a radical? Again, to differentiate these, first classify what the hybridization of the carbon. You have sp3, sp2, sp3, sp3. So immediately we can eliminate HC because that's going to have a higher CH bond association energy. So the remaining sp3, you go ahead and classify them. HD is primary, HB is secondary, HA is primary. So you have to recognize that typically the order is going to be tertiary greater than secondary greater than primary. But HD is a special kind of primary. It's allylic. So that hydrogen is most going to be readily abstracted because it forms an allylic radical that is resonance stabilized. Question 8 says, which of the following arrow-pushing formalisms represents the fastest rate-determining step in an SN1 reaction mechanism? So remember the rate-determining step for SN1 was ionization. Of the leaving group. And so what are you doing in that? You are forming a carbocation. So what you want to do for each of these is classify the carbocation that's being formed after the arrow pushing. For A, you have a tertiary. B, you have secondary, but you have a poor leaving group. C, you have primary. D, you also have tertiary. So you have two tertiaries, and the rate of SN1 follows the order tertiary greater than secondary greater than primary. So we can eliminate B and C. Now you can differentiate between A and D because D is benzylic. So the difference between the two is that the benzylic carbocation is resonance stabilized. So that's more likely to form faster. How many unique products would result from the monochlorination of the following substrate? So this molecule has an element of symmetry. And basically you're going to determine the unique sets of hydrogen. So you have 1, 2, 3, 4. You have 4 unique sets. So if you substitute one hydrogen from each of those, that's going to give you 4 different monochlorinated products. So the answer here is A. Question 10 says the SN2 reaction involves nucleophilic attack 180 degrees to the departing nucleophile resulting in inversion. Which of the following substrates would demonstrate that such an inversion has occurred? So you're basically being asked is if you had to test the hypothesis that inversion does occur, which substrate is best for that? So you need one that has a chirality center. Because if you have 2 equivalent groups, you're not going to know that inversion has occurred. So you would draw these out. So A, you have bromomethane. That does not have a chirality center. B is 3-bromopentane. This does not have a chirality center either. C is 2-bromopropane. This does not have a chirality center, and D is 2-bromobutane. So this does have a chirality center. So you would be able to tell if when you reacted that with a nucleophile that inversion did indeed occur. So we have a reaction coordinate for the next couple problems of energy versus time, or the reaction coordinate. So which points on the diagram represent transition states? A transition state is always the highest point. So in this case, it would be B, D, and F, which is B. Question 12 asks what points in the diagram would represent intermediates. Those are the wells, so those would be C and E. 13 says, what is the free energy activation of the reaction? So again, that's the energy of activation is from your starting point, this line, to the highest point. So that's going to be to point B, which has to proceed through energy H. So our answer here is C. Question 14, overall the free energy of the reaction is, since the free energy of the reaction, the products were lower than the starting materials, the value is G, and it's exergonic, since we're talking about free energy specifically. So the answer here is D. 15 states which nucleophile best matches the IR given. So within this IR, you can see the main peak that we're looking at here is this OH stretch. There's nothing in the carbonyl region. So the best answer for this is A, which is methanol. 16 states which bromide will ionize fastest to undergo substitution by a SN1 mechanism. So we classify them. We have sp2 hybridized carbon, so that's out. For B, we have a secondary sp3. C, we have secondary sp3, that's allylic. D is secondary sp3. So if we're considering how we would resolve between all of the secondaries, the secondary allylic is going to be the fastest due to stabilization by resonance. 17 states which reaction would produce phenyl propyl ether. So this is an SN2 reaction, and you're looking for a good nucleophile with a good electrophile or a good leaving group. And if you look at what's above the arrow in each of these, you have the 3 carbons that are going to belong to the propyl, the nucleophile or potential electrophile to the left is supplying the phenyl ring. So you're looking for a combination of something that's going to be the nucleophile with a good leaving group. And so A is out because you have a good nucleophile, but you have a poor leaving group in OH. B is the correct answer because you have a good nucleophile with a good leaving group, bromine. C and D are both out because you have sp2 hybridized carbon bearing a leaving group, bromine. And you know, one of the criteria for SN2 is the leaving group carbon being sp3 hybridized. 18 states, what is the specific rotation of the alcohol produced by the bimolecular nucleophilic substitution? So you are going to get an inversion. So what you're looking for is hydroxide is going to attack this carbon bearing the leaving group. And what you're going to end up with is the enantiomer of this compound that's drawn. So if you're given the specific rotation is negative 9.9, and you're looking for this specific rotation, it's going to be the enantiomeric value, which is D, which is B, dextrorotatory 9.9. Question 19 states, which of the following choices has the substrates listed in the proper order for SN2 reaction? So the rate of SN2, again, is primary greater than secondary greater than tertiary. So if you look immediately of the first choices listed, you have 3-chloro-3-methylpentane. If you draw that out and then classify the carbon bearing the leaving group, so 3-chloro-3-methylpentane, that's tertiary. That's going to be out. For B, you have 1-chloro-3-methylpentane, that's primary, so you have to consider it. Then you have chloromethane for the next two. So between B, C, and D at this point, you can eliminate B because chloromethane is going to react faster than 1-chloro-3-methylpentane. So now you're looking at the next two in the series between C and D. You have (2-chloro-3-methylpentane, which is secondary, versus the 1-chloro-3-methylpentane, which we saw before as primary. So at this point you can eliminate C, and D is going to be your correct answer. So this is essentially going to be a methyl substrate. This is going to be primary. This will be secondary, and then that'll be tertiary in terms of classifying the carbon bearing the leaving group. Question 20 is asking you, what is the propagating radical in the free radicals chlorination mechanism? The propagating radical is going to be C, and that is the radical that's formed that ends up going back into the first propagation step. This is propagation 1. This is propagation 2. And D is not a radical, so you can eliminate that. Question 21 is a ranking question. So this is SN1 from fastest to slowest. So again, the rate trend for SN1 is opposite of SN2. So tertiary is greater than secondary, is greater than primary, it's greater than methyl. So what you need to do is convert these names into structures and then classify. So you have 1-iodo-2-methylhexane. So here's compound 1. Then you have (3-iodo-2-methylhexane), that's compound 2. Iodomethane. And then finally 2-iodo-2-methylhexane, that's compound 4. So classify them. This is primary, this is secondary, this is methyl, this is tertiary. So when you look at the order, you need compound 4 to be first because that's going to ionize the fastest. So we look at our answers, we can eliminate B, C, and D. And that's going to follow the rate. Compound 4 reacts faster than compound 2, which was secondary, which reacts faster than compound 1, which was primary, which reacts faster than compound 3, which was methyl. 22 is asking you what is the product of the unimolecular substitution reaction. So this is SN1. So go ahead and draw this compound out when it's hydrolyzed in water. So let's convert this name to a structure. We need a pentane. There's our 5 carbons. Carbon 3 has a methyl group. Carbon 2 has a chloro. So even though this compound is showing stereochemistry, what you can do, if you consider the mechanism, is just show the ionization at this point. You now have a secondary carbocation, and you know that secondary carbocations can rearrange, and that's what this will do with a 1,2 hydride shift. So when that happens, you're going from secondary to tertiary. You now have a tertiary carbocation. So what you started off with in terms of chirality centers, carbon 2 is destroyed in the ionization. Carbon 3 is then destroyed in the rearrangement. So you're ending up with something achiral. And we know that when the nucleophile attacks, it will attack both sides of the p orbital. But even more importantly, in this case, you're still ending up with a compound that does not have a chirality center. So the answer for this one is C, 3-methyl-3-pentanol. (23) is asking which of the following radicals react the fastest. So what does this mean? This means it's the least stable radical. And so when we classify these, we have tertiary. This is an sp2. This is tertiary. This is secondary allylic. So A, C, and D are all stable. B is not stable, so it will react the fastest amongst those. 24 is asking you about the reaction shown. What is the commonality? It's an SN2 mechanism, so that's a clue. So the first thing you have to do based on the choices is determine the name of the starting material. And so the way you do that, the trick here is you're given a Newman projection. So the chirality carbon is the carbon in back. Bromine is going to get priority 1. Fluorine is going to get priority 2. The carbon in front is 3. This hydrogen's 4. So if you consider putting the lower priority group in the back, you're going to be going in this direction counterclockwise, so that's S. So you can eliminate A and D. So at this point, the S1 bromo, 1 fluoroethane is the same for both. Now what you have to do is consider what is the CIP designation of the product. The SN2 reaction occurs with inversion. So you'll notice the fluorine is now ending up on the opposite side after inversion. So in this case, you have to consider the chirality center of that rear carbon again. Fluorine takes priority 1 over oxygen 2. The carbon in front is 3, and the hydrogen is 4. So again, when you do that, you end up counterclockwise S. So when we look, we can eliminate now B, because the R is not correct. We have to have S and S, so the correct answer is C. For 25, it says rank the following carbocations in order of decreasing stability. So the most stable is first. What do you want to do for this? Let's classify. Compound 1 is sp2, 2 is secondary, 3 is tertiary, 4 is primary. So when you look at your order, tertiary is the most stable, so this has to be ranked number 1. So we can eliminate choices A and D. The next most stable has to be compound 2, so we can eliminate C, leaving B as the correct answer. So this has been a screencast on exam 3 review of substitution reactions, including radical SN1 and SN2 for the spring 2019 semester of Organic Chemistry 1. If you like this screencast, please hit the like button. If you want to see more content, please subscribe. Leave a comment if you found this screencast useful.